All right, what's up, everyone? We are a little delayed here, but we are in fact live. It is Thursday, which means that we are doing some live Leetcoding, and we're going to go ahead and get right into this one. As always, what I'm going to be doing is pulling up a recent Leetcode contest. This one, it looks like we're doing contest number 289. So I believe this was from, I want to say the week before last. So we're going to go ahead, go through a couple of the problems in here. I'm going to just be walking through the problems live, showing you my thought process, showing you how I approach these problems. And as we go through this, I really want you to see, how do we think about these problems, right? This is just repeated exposure at this point. If you've been coming to these lives with any regularity, you see what are the patterns that are repeating? What are the things that we do differently time to time? How do we address cases where, okay, here's a problem and I don't really know how to approach it? So I want you to start thinking about, how do I do this in my interview? And how can I approach these problems that I've never seen before? So with that, let's go ahead and jump over to Leetcode here, and we'll go ahead and get started with some of these questions. So in this case, let's go ahead and, I think we'll get started with the second one again. I think this makes more sense than starting with the first one, because the first one tends to be a little bit too easy to be super interesting. So let's start with number 2 here. All right. And as always, if anyone has any questions or if there's anything that you're wondering about as we're going through this, go ahead and put that in the chat. I'm always happy to talk through stuff, answer any questions, anything like that. So in this case, we're given a 0-indexed integer array tasks, where tasks I represents the difficulty level of a task. In each round, we can either complete 2 or 3 tasks of the same difficulty level. And then we want to return the minimum required rounds to complete all the tasks, or -1 if it is not possible to complete all of the tasks. Okay, so in this case, we are given something like this, where we could do merge, well, let's see, I guess the first round we would complete all the difficulty 2 tasks, so we would have 3 tasks of difficulty 2. Then we would do all the tasks of difficulty 3, and then now we have 5 tasks of difficulty 4, and so that's going to be 2 rounds. In this case, we're only given 1 task of size of difficulty 2, and so we can't complete it because we are not going to have enough tasks of difficulty 2, and we have to complete 2 of them in a round, right? So essentially, where we're going to run into issues here, and where this is going to be -1, is if we have exactly 1 of any task. Because as we're thinking about this, let's consider our possibilities here, right? If we have 2 tasks, we do it in a single round. If we have 3 tasks, we do it in a single round. If we have 4 tasks, we do it in 2 rounds, right? Because it's going to be 2 and 2. If we have 5 tasks, it's going to be 2 rounds, because it's going to be 2 and 3. And then we can really just repeat this process, right? Any larger number, we can reduce it down to some number between 2 and 5 for sure, right? Like if we can either decrease, but we just repeatedly decrease by 2 or 3 until it ends up within that range, and then we know it's solvable. So anything, unless we have exactly 1 task of any type, it's going to be solvable. And then really, the amount of time this is going to take is going to just be dependent on the number of, total tasks we have, right? So honestly, we could probably even, if we really wanted to do this, pre-compute for different numbers. I'm just trying to think if there's an easy way for us to figure out how many total tasks there need to be. And I actually, now that I think about it, I think there is a solution. But essentially what we need to do is we'll need to start by by figuring out the number of tasks of each level of difficulty. So let's say that we have this. And we can do this, we can just use a map probably to count these all. So we'll have this, and then we'll have a map where we have 2 maps to, there are 3 occurrences, 3 maps to 2 occurrences, and 4 maps to 5 occurrences. Right, and then the question becomes, for each of these, how many turns does it take? And so if the number is 2 or 3, then we know that it's exactly 1. If the number is 1, then we know that our result is invalid. I should change this. then we know that it's invalid. And let's say that we get bigger than that. Well, essentially what we want to do is like we're going to want to remove, like we're going to want to combine sets of 3 tasks at a time, right? Because that's going to reduce our amount the fastest as possible. So essentially what I think we can do is I think for any number bigger than 4, or actually for any number, I'm thinking could we divide by 3 essentially? I think that we could divide by, or like do a mod of 3. Like if we divide by 3, let's say that we had 25 tasks. Let's just look at an example. If we divide by 3, then that's gonna give us 8, right? That's gonna give us 8 because it would be 24 and then we have 1 left over. So 25 mod 3 would be 1. Now, that means that we can do 8 sets of 3 tasks, but because we have exactly 1 left over, that's not actually valid, right? We can't do 8 sets of 3 tasks because then we have 1 left over, which messes us up. But what we could do is 7 sets of 3 tasks, and then that would leave us with 4 left over. And so we would do 2 sets of 2. So I think what we can do is do this number divided by 3, and then if this, and then it's basically, we'll do that number mod 3, and if we get 1, then we have to add 2 to our initial result because we have to, actually no, we don't even have to. We just have to say, if there's a remainder, add 1, right? Like if this is not equal to 0, then add 1 to 8. So we would get 9 because it would be 3 times 7, which would be 21, and then 2 times 2, which would be 4, right? So 7 plus 2 would be 9. So really that's, I think, all we have to do here. And then the question just becomes, okay, we need to count the number of these, and then we need to do this math and count them all up. I'm trying to think, in terms of collecting all these, I mean, the obvious answer is to just use some sort of map and count them all. We could also, we could sort, and then we wouldn't need to use any extra space potentially, but that is going to take longer. So I think that the answer, and then we don't have a clear, like these can be, we have a huge range of numbers. So I think it makes most sense for us to just count them all. So let's do that. We'll do a hash map. Well, let's call map of integer to integer. Counts is a new hash map. And then, there is I keep forgetting that I can do this, but there's this get or default, right? I think that's probably the easiest thing for us to do here, because what we'll do is for, we'll say for int I in tasks, and then in the map we want to say our current count is going to be I.get or default. Because we get the value and then we increment it if we need to. Get or default, and this should be not I, but counts.get or default I and 0, and that way we just say counts.put I and C plus 1. Right, so we increment it. There may even be, I don't know if there's an even more efficient way to do this, because that does seem like a kind of thing that, like incrementing a value in a map would be something that would be useful, but that's fine. And then all we have to do is iterate over our, iterate over the map and basically count. So result equals 0. Now for, I think we can just iterate over the entry sets, right? So for E in counts, we're going to iterate over all of these entry sets, and we're just going to get the get that value, right? So in this case, if I remember how to do this properly, I think we can do the other way. I always forget the actual syntax for this because I don't do this enough. But it's going to be something like result plus equals e dot value divided by 3, and then mod 3 is not equal to 0, result plus plus. Right, it's basically that, and then we return the result at the end. I don't think that syntax was right. So just pull this, it's, yeah, okay, so it's entry in counts.entry set, and then I believe it should be actually get value. Basically what I had. All right. Yeah, so I mean this, the reason that I wanted to do this is last week we had a similar one, and all I did was I got the key set and I iterated through and got them for each one, and that's really probably not an efficient way to do this. It's definitely going to make more sense for us to iterate over the entry set from the standpoint of how do we as efficiently as possible iterate over all the values in our map. So in this case, you know, this seems to work for this case. I think our logic is sound, so it's just going to be a question of did we miss any edge cases here. Oh yeah, so I didn't actually, I didn't handle this where what I should have said is actually if e dot get value, like if the value is ever equal to 1, then our result is invalid. So I should just return -1, right? I can immediately break out of it if that result is equal to 1, right? So, okay, that worked there. Let's take a look here. All right, this is kind of slow. Where did we fall in the memory distribution? I don't know. 110. Okay, so this solution doesn't look very good. I'm trying to think, is there an obvious way that we could optimize? I mean, like using there's probably, you know, doing all this is not the most efficient. I'm not super worried about this because because I mean the time complexity is fine. I'm wondering what specifically is, I'm wondering either what is slowing this down significantly, or alternatively, is there a significantly better way to approach this that I'm completely overlooking? Right, like the obvious answer is that anytime we're working with objects like a map, it's going to be relatively slow compared to what we could be doing instead, right? So if we could do this without using a map, so it's possible that if we sorted this, for example, that would be even faster, even though we didn't. Even though the complexity would be worse. I know that in languages like Python, there is, I believe, also and you might be able to do this in Java too, especially with like a stream or something. I'm just not sure exactly how. To get the counts of all the to count the occurrences of each thing as like a single line. Yeah, I don't know. I'm curious. Is there anything specifically different here? Okay, that's not different. And then that's not different. Okay, so, you know, see, this is interesting. Like, as we look at this, the code is basically, like, I just picked a random example here. This code does basically exactly what we're doing. The only difference is that they're actually doing what I said I didn't want to do, which is iterating over the key set and then getting each one. And then, again, they're doing the same thing. So I guess they have this broken out into, this is a single operation, but shouldn't make a difference. What I'm gonna try, I'm curious to like submit this again and see if we get significantly different runtime. Then otherwise I'm gonna let it go. No? Okay. Yeah, I don't know why ours looks so different from that other solution that basically looks the same. But all right, well, moving on. And again, I guess for the complexity of that one in general, we have basically an O of n time complexity and an O of n space complexity, right? Because if we go back to this for 1 second, we are iterating over that array. So this is going to take O of n time, and then this is going to take potentially O of n time again. And then we're using O of n space to store this, right? Like the worst case scenario is that we have all unique values, and so it takes O of n space because we have to store, it takes n space because we have to store every value separately. Can I explain why they're doing value plus 2 divided by 3? Yeah, so that's a good question. So when they have this value plus 2 divided by 3, right? This is basically, it's doing the same integer division that we're doing, but we're essentially shifting by a couple. So like, let's think about what we actually are doing here. When we're doing this, I'm breaking this into 2 steps, where I'm saying essentially, if the remainder is equal to 1 or 2, I want it to be 1 greater. And in the case where the remainder is 0, then I want it to stay the same, right? And so essentially what this results in, I mean, the easiest way to see this is to just draw it out. So like, let's say that we have our example of 25 again. So 25 divided by 3 is gonna again be 8, and then 25 divided by, or mod 3 is equal to 1. So we're gonna do the essentially 8 plus 1. Now, what we can also consider is what this is going to do is it's basically going to shift where that single value that we don't look at is, right? It's going to shift the result of what mods to 0 essentially, and it's going to shift where the cutoff is. So essentially, what we want to do is we want to shift the cutoff. Like I don't know a good way to explain this exactly. Again, I think examples are the easiest. So like if we look at 26 divided by 3, that becomes 8 again, and 26 mod 3 becomes 2. Now if we have 27 divided by 3, that becomes 9, and 27 mod 3 equals 0. And so essentially what we had is we shifted up by, when we shift up by 2 like that, when we increase it by 2, we're saying that the 2, we have this circular thing, right? We basically rotate around that mod. So it goes, mod 0, mod equals 0, mod equals 1, mod equals 2, mod equals 0, mod equals 1, mod equals 2, and it just keeps rotating around. And so if we, and then where the cutoff is changes. So essentially if I have, in this case, if I had 25 divided by 3, I'm going to get 8. But once it gets to 27, now I have 9, which is my full result. And if we repeat this process again, let's say that we had 28 divided by, let's say that our actual result was 26. So we wanted to, and we consider an example, if we have 28 divided by 3, that is going to give us 9 again, which is what we wanted. And so I guess I don't really know how to describe it much better than that, other than I'd recommend going through some examples and working through it, and you'll see how that works. Do you need to do that sort of thing? Not really, but it's like, it is a helpful little like kind of hack that you can use when you end up in these situations where it's like, okay, I'm modding these things together, and I'm trying to sort of shift it in that way. I don't know if that makes sense, but hopefully that at least gives you some more context. Like that's one of those things where, if you're trying to figure out even what to do in your code, I would just test a couple different things and see what works. All right, let's look at this one. So we're given a maximum trailing zeros in a cornered path. So we're given a 2D array, an m by n array where each cell contains a positive integer. A cornered path is defined as a set of adjacent cells with at most one turn. More specifically, the path should exclusively move either horizontally or vertically up to the turn without returning to any previous visited cell. After the turn, the path will then move exclusively in the alternate direction. Okay. The product of a path is defined as the product of all the values in the path. Return the maximum number of trailing zeros in the product of a cornered path found in the grid. Oh, like trailing zeros like in the product itself. I see. So a cornered path. Let me go back to this definition. Set of adjacent cells with at most one turn. Oh, I see. These are, I was like, don't these second two like disprove that? But those are both not valid, I think. I think that the point is that the first one is the only one that is a valid cornered path, which is what I was thinking. Yeah, okay. It has more than one turn. That's what I was confused about. Okay. So the grid on the left shows, okay. Yeah, so the product in this case is this, which we have 3 trailing zeros. Okay, fine. And now, yeah, so like, I was gonna say, like, we could come up with a bigger path, but like, it wouldn't actually give us more trailing zeros. So like, we could go 23, 17, 5, 26, 1, 4 would be a bigger product, or like going across the top and down the edge would be a bigger product, but it's not going to have more trailing zeros because it's gonna end in like, it might end in A0, but it's gonna end in like mostly other stuff. So fine. In this case, there are no cornered paths in the grid with a product with trailing 0. Okay, so the result would be 0. Okay, yeah. And if we think about like, so there's a couple. How do we identify a cornered path? The other thing is that how do we count the number of trailing zeros, right? Because we don't necessarily, like if we can avoid it, you know, our grid could be very large. Our grid could be, yeah, pretty massive. So we don't want to consider every possible, or we don't necessarily, like our product could be super large. So we don't really want to do that. We don't really want to deal with we don't want to necessarily track the whole number, right? And we need to figure out what is a trailing path here, or what is a cornered path. So our kind of brute force solution to this, I mean, I think this should hopefully be fairly self-explanatory, but the brute force solution would basically be, let's try all of the cornered paths and determine the number of trailing zeros. And maybe another way to think about this is like, yeah, so we could find all the cornered paths, which would basically be like, if we wanted to do that, we would start by, we could just do 2 groups, because either the cornered path can either goes across first or down first, right? And so we could write, we could find all the cornered paths that go across first and then down first, because basically we start in every cell and then we go across however many and then down however many, right? And I guess the other way that we could do it is we can, any 2 cornered paths, we can define all our cornered paths by looking at the 2 corners, at the 2 ends of the path, right? And then if we look at 2 ends, so if we look at, like in this example, if we look at 4 and 8 in the 8 in the bottom right hand corner, there are 2 cornered paths. There's either you go across and then down, or there's you go down and then across. And so we could go through all of the cornered paths by doing that, right? By looking at every pair of cells in our grid, and I can draw this out because this will probably be easier if I do. But by looking at every corner in the grid, or every two pairs, and then when we look at each pair, we're going to calculate, okay, what is the find both of those paths, right? We'd have to write a function that would figure this out. It's not going to be trivial to do, but we could do it. It's not going to be impossible for us to do this. So again, like what we could do here is we have some sort of grid, and then let's say that we look at like, okay, this square and this square. Now we have two paths, right? We have the path that goes like this, and we have the path that goes like this. And now I think also, I guess like the other thing that we know is that these can't be in the same row or same column, because it's not just a cornered path, or it's not just, it can only have that. Wait, no, okay, it can be straight. So like just a single line counts. So they can be in the same row or same column, which is good for us to know. Now, the other thing that I'm thinking, so we could do this, we could generate all these, we would basically end up with n squared times n squared, right? Different possibilities, because every pair of these, there's n times m times n times m. So we basically get n squared, I guess really O of n squared times m squared, different combinations. And then for each of those, we would iterate through it. I mean, that's going to give us an additional, the longest path we could have would be m plus n. So it would be times m plus n kind of thing, would be like our complexity of doing this, which is not great, obviously. And what I'm kind of thinking here, and here's like my one thought, is would I ever want to consider a cornered path that doesn't go that doesn't go as far as it can in a certain direction? So what I mean by this is, like, let's say that instead of this, I don't know, so maybe I should just redraw it, but whatever. Let's say that instead of this, I had this. Now my path looks like this, but is there ever any reason that I wouldn't include these two extra cells or this extra cell? Is there ever a reason why doing that would create fewer trailing zeros? And the answer is, I think no. I don't think there's ever a case where that would reduce the number of trailing zeros. Because what is it that gives us trailing zeros? What leads to trailing zeros is one of two things. It's either one of the numbers in our grid has a trailing zero. So like you have a 10. 10 has a trailing zero already, or 20 has a trailing zero already, and so that adds a trailing zero to the total, right? We know like when we multiply 10 by any number, we shift the decimal point by 1, right? So we add a trailing zero. And the other case where we get a trailing zero is if we have two numbers that multiply to something that has a trailing zero. So like, for example, if we had 5 times 2, that gives us a trailing zero. But if we had 5 times 3, that would not give us a trailing zero, right? Because it multiplies to 15. So even though we shifted the decimal place by 1, it's not giving us a trailing zero. And so with that in mind, I'm trying to think, like, any other number, if we have two numbers that, like, let's say that we have a number that's a multiple of 2 and a multiple of 5, I think that also creates a trailing zero. So like if we had 15 times, so that's a multiple of 5, times 2, that would be 30, right? Okay. So that would give us a trailing zero. But the other thing is, like, okay, I don't think that this is going to be an issue, because I think that we can narrow our search down significantly, because I think that it's the transitive property, right? The order in which we multiply these isn't going to matter. And if we multiply anything times a number that has a trailing zero, that trailing zero cannot go away, right? That trailing zero is never going to go anywhere, because it's just going to get multiplied by zero. So I'm pretty sure what I'm thinking is, I think that we can look at like basically cells that are only around the borders of our grid. So for example, we can look at only L's that, like if it's an L shape where it goes down and then across, it has to start at the top of the grid, and then it has to end along the right side of the grid. And then if it's the other way, it has to start along the left side of the grid, and it has to end along the bottom of the grid. Because otherwise, because we're basically that is if we just look at those, it contains all the other ones. It contains all the smaller L's. If we look at that set, but that's the thing, is if it contains the other L's, then I don't think that we're going to lose any zeros by doing that. Right? At most, we end up with no additional zeros. Is there a better way that we could do this? Because like, okay, so if we do that, if we say that's the case, I can write a function that's just going to iterate. It's going to iterate across and then iterate down for every start and end point, right? Or really for every row and column that we choose. And then it's gonna, the simple version is we multiply them all out and, use a long or something, and then we hope that it doesn't overflow. The next best option is that I think that we could probably truncate a lot of stuff. Like we could truncate any trailing zeros and just count them, right? We don't need to, the trailing zeros are going to remain the same unless they're only going to get added in. So we could do that, which would keep our numbers smaller, but I think we can also probably truncate the large end. But the other thing that we can do is look at like, what are all the numbers that we're passing in that are either 10, that we're multiplying through, that are either 10 or a multiple of 10, or 10 or, multiple, like 2 5 pairs, right? So like there is a way that we can, I don't know how easy it's going to be for us to do that, but we could try and just directly count what is going to be the number of zeros. Now, the complexity of doing this, let's see, we're basically iterating over the whole grid twice. So at least this way, we're going to end up with our iteration over the grid. There are, O of n times m different pairs, right? And then it's n times m, and for each of these, it's n times m plus, or times m plus n. So I mean, obviously this is a lot better. I don't think that is super inefficient. I guess like the only question is, can we optimize this? Can we either come up with a greedy approach or maybe a dynamic programming type approach? Because right now we are just generating all the paths. So hypothetically we could, that might be an option for us. I don't think that we can do a greedy approach because we don't know what's going to occur later in the array, right? So if we started at the top and we we said like, okay, let's start at some spot and then greedily choose the next step, we're not going to know what the, we don't know like maybe, okay, the best path is this way from the initial part, but then there's a lot of really big numbers down here and we just don't know that. Right, so that kind of rules out, I think, just a strictly greedy approach. Dynamic programming, I mean, maybe we could do something, like we could just essentially, again, we're trying all the possibilities. I guess like what we could do is the problem with that is that you don't know. We'd have to differentiate between the different directions because I think dynamic programming would be a lot easier if we were talking about like every possible path. And I just don't know that that's really necessary in this case. I think that each of our paths is like, we've already, by doing this, by reducing all these extra parts, we've kind of reduced this down to basically looking at, there's like some overlap, but like we've removed as much of the overlap as we can, I think. So I'm not even sure that we really want, I don't see offhand like a better way of doing this than just trying these different possibilities. Let's implement this, and I'm gonna implement this first without doing anything fancy trying to compute the number of zeros. I'm just gonna multiply it through everything. I'll break that out into a separate function so that we can experiment with it later. But for the moment, let's just try coding up this iteration. So what we have is we want to iterate through, I guess like we have two different groups of things. We have the L's and we have the, I don't even know what you call that, backwards L's. So let's go ahead and this part is easy for now. Actually, no, it's not. We can't really break that out into a separate function because we're just gonna do it as we go along. So okay, fine, whatever. So let's do the so our max trailings are max, and then so let's start by doing the L's. So what we want to do for the L's is we want to consider, we're going to try starting in all the columns, and then we go down to the column and then across the row. So I'll do column equals 0. The number of columns is equal to grid 0.length and call plus plus. Plus. And so what we do is we iterate, so we have basically the pair first, and then we do the iteration over it. So we say, we're going to basically, for I equals 0, I is less than, so we're doing the L. So first we go down. I guess really, no, this is fine. So for I equals, maybe let's initialize this to the initial value. We're going down the rows first. So row I plus plus. Times equals grid I. This is weird. I column, and then we do I think I'm gonna do this because I think that what I'm doing, I think I actually want to start this at 0, and then I'm gonna start this at 1. I'm gonna go back on what I said before about that, and then basically that's gonna go. So what's gonna happen here is let's consider an example, because it's this is a little weird. So if we grabbed, oh, they don't have us. Let's look at this one. So if we have this, and let's say that column equals 0 and row equals 1, what's going to happen? So first, I is equal to 0. So if column is equal to 0 and row is equal to 1, we want to go from here, we want to do this one, then this one, then this one, then this one, right? Like that's the path that we want to take. So we're gonna get I equals 0, row is, I is less than row, so we're gonna do I column. So I is 0, row is 0, so that's the first value. Then we increment it and we break out of this. So we start and we go across, and this should be probably, I think this needs to be less than or equal to column, because basically by having this be less than and not less than or equal to, we don't want to double count this 7, right? Like that's kind of the thing that I'm trying to avoid. But if we do it this way, now we're going to get row is going to be 1, and then I is going to be 0, 1, 2, this should be grid dot length, or grid 0 dot length, and then it does become less than. Now our other direction, so I'm pretty sure that's right, and then what we just need to do is in here it's like, okay, I will have a stub this out for now. So this would be trailing zeros equals math.max of trailing zeros and product. No, wait, trailing. I'm going to not reuse this variable name. So it's going to be this, and then, you know. Now, you know, this, so that's the one direction. And then for the other direction, it's kind of just this in reverse, except that, you know, we, instead of, we can probably iterate over, like we can reverse this. So it's going to be we're going to start with the rows. We're going to pick row, 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 row. And I mean, does this actually matter which order we do this in? Not really. But I want it to be consistent. So, and this will be column. So now what we're doing is we're starting by going across and then we're going down, right? So I is equal to 0, I is less than column now, and I plus plus, then this becomes row. You know, it's just kind of, again, this is just like inverted. So now it's going to be, now we iterate across the rows. So it's going to be I and column. And then ultimately at the very end here, we're going to return trailing zeros. Now, obviously, this is not implemented right now, but what I'm curious, or like not all this is implemented, but what I'm curious is to see, is this calculating the right values here? So what I kind of want to do is just print out some stuff and see. So I'll print out that. I'll do that again down here. If we run it. Okay, so all of our products are ending up as 0, so that's obviously not right. That's weird. The product should never be 0 unless we're, or, oh no, that's why it should be product, not trailing zeros. Okay, so let's just consider this for a second. So if this first one, we're doing the L's, right? So row, column. So 0, 0, that basically is just, that should be the product of iterating across this first row, right? And I'm just gonna pull up the calculator on my phone here to double check, but we get 23 times 17 times 15 times 3 times 20 is gonna be, yes, that's correct. Now, in this case, I'm going, I have row column listed, right? So I'm gonna go to the second row and then go across. So it's gonna be 23 times this second row here, which is gonna be 8 times 1 times 20 times 27 times 11. I get this saying, I do get this correct value. Now let's, so that feels like, that seems like it's working okay. I wanna try the other variation. So let's say that I got, let's look at this one here. Or let's actually look at this one here, which is I go over one and then go down the column, right? So it's gonna be 23 times 17 times 1 times 4 times 9 times 7. I get 98. Okay, yeah. So I think that all seems to be working okay. And now, you know, I can see in these, obviously, like all these different variations with trailing zeros. I see, you know, this one has 4 trailing zeros. So that seems like that should be, what's the top, what's actually the, okay, it says the answer is 3 though. So maybe I should double check this one because this, so this was, okay, if it's row 3, it's the L, it's row 3, column 2. So I'm going column 2, I'm doing 15 times 20 times 6, that's row 3, or that's row 2, times 1 times 10 times 6. Okay, that didn't line up. So let me, I'm gonna, it's like really hard to do without kind of sketching out a little bit. So let me just copy this up above. Some of the spacing. we're close enough. So then it was this one that wasn't right. So it's so we could, right, I'm printing out row column, and then so row 3 is going to be this one, and column 2 is going to be this one. So it's 15, 20, 6, 1, 10, 6, right? Should be the path. And I'm pretty sure, so 15, I'm pretty sure I did this right. 15, 20, 6, 1, 10, 6. I get 3 trailing zeros, and I get a very different result from this here. So what is it that is being, what is it that's we're doing wrong here? That's my question. Well, let's walk through this. This is a good opportunity for us to just kind of walk through the code by hand and see what's happening. So I have product equals 1. Now here I equals 0, so we get product times equals grid 0, 2. 0, 2 is going to be this one. So times 15. Now we increment I becomes 1. 1 is less than row 3. So I get 1, 2. So it's going to be row 1, column 2, which is this. I is going to be 2, which is less than row. So I get 2 and 3, or 2 and 2, which is this. So times 6. Now I is going to be equal to 3, which is equal to row, so we break out. Now we come down here. I is going to be equal to 0 again. Oh, that's why, because this should start at column, right? So this shouldn't be starting at 0, this should be starting at 2. And it was starting over here, so we're multiplying these 2 into the whole thing. And the same is going to be the case here, where this second one shouldn't start at 0, it should start at row. So let's try that. Alright, this looks a lot more promising. This looks like, yeah, I'm seeing good results here. So how do we get the number of trailing zeros here? Just to, the easiest way to do this is going to be sum equals 0, is to keep dividing by 10, right? So while num is greater than 0, and we'll just say if num mod 10 equals 0, sum plus plus, or I can say if it's not equal to 0, break, else we're going to do sum plus plus and num divided by equals 10, right? And then we just return the sum. So in this case, we do get the correct answer. I don't think that this is going to, I think that the issue that we're going to run into is going to be some either time limit exceeded or not like memory, but we might get an overflow on our long. It might work. But yeah, okay. So in this case, yeah, I would guess that we're just getting an overflow. Like these numbers are big enough that and so this is where, okay, we have a couple options, right? We can try and just count the number of zeros. And the way that we could do this, here's an idea, is, again, remember that what we need to do is we need to count either the tens or the numbers or the number of values that are divisible by 5. And so here's my thought for this. Is we could essentially, and I guess we're gonna have to do this like for each one of these, but like, here's my idea, is like if we were to just count the number of occurrences of if we were gonna count the number of occurrences of numbers that are divisible by 10, divisible by 5, and divisible by 3, then, or divisible by 2, then we would be able to basically take that and count the total number of zeros. Because we would end up with, okay, the tens each result in a 0, and then for the number, and then basically the minimum of the 2s or the 5s becomes the other 0 count. That also doesn't take into account numbers that are divisible by something like 10 multiple times. I think we would have to keep, I think for each number we would have to divide it multiple times. And I mean, the question still becomes, is this necessary? But okay, here's my, like, I almost feel like what would make sense is to implement like, and here's what I'm gonna try. So our 0 counter is going to have a like this is basically all I need to keep track of, and then I'm gonna have a I'll initialize it. Doesn't actually need to do anything in there because those will automatically get initialized to 0. And then and then what I'm going to do is I'm going to take in a number. So and then what I'm going to do is essentially we're going to divide it by 10 as many times as we can and increase tens. So it'll be like while here's what it looks like. While num is greater than 0 and num mod 10 is equal to 0, tens plus plus and num divided by equal 10. Now, next we do while num is greater than 0 and num mod 5 is equal to 0. We do the same thing. And then finally, we do the same thing for the 2s. And with the 2s, I mean, there's probably a better way that we could do this, but I'm just like, you know, I just want to keep this simple, so. So we do that, and then we just have a, then we can compute the number of trailing zeros. And what that is it becomes return tens plus math.min of 5s and 2s. So what we have is, now that I've created this, I can do this much more easily, because I'm gonna say, I'll still do this, and then I'll just, here I'll do 0 counter ZC equals new 0 counter, and then here this becomes ZC dot add the number, right? Or add number. And this becomes again. Now again, is this necessary? Probably not. And then this becomes ZC dot trailing zeros. Right. Now this, we do the same thing below, like we do the same thing again. And the question is, does this work? Well, it looks like it worked for that one. Okay, so we're still getting the same issue here now, which is making me a little concerned that there might be something else going on. I mean, I do think I should make sure that I updated this all properly. I can also print this out. So and then we can print this out and see what we're getting. Should grab this, I guess. So I guess, yeah, like my question becomes with this, just like where are we, I'm not clear looking at this input where we're actually missing something, right? Like it's, obviously we are missing something, and I do still think that it's probably an issue, or like, I don't know. I guess I'm not sure like what the, I should just do this. We lost our test case here. Like, are we considering all the possibilities? I guess like the question becomes, one, are we considering all the possibilities? And two, are we maybe miscomputing? Like maybe, okay, so I'm noticing this. Is this a 1, 2, 3, 4, 5, 6, 7 rows and 6 columns? Doesn't look like maybe we're going through all of the possibilities. Is that right? Like it looks like we're going through, there's 7 columns or 7 rows, and then are there, oh no, we are. Then there's 6 columns. 7 rows, 6 columns. Yeah, I mean, this is one of those ones that's like super awkward to debug, right? Because I don't actually have any idea why it's not working, and a lot of the other cases are working. Like this was the 31st test case out of like 51, so other than just walking through the code and looking for mistakes, or if we could figure out, like if we could figure out what the expected path for this should be, that would be helpful, because I don't know right now. Like I guess I can, let me copy this over. So I don't know at the moment what which path is the one that actually gets us to our target. We want 6 zeros. So I guess if we look at this, like if we just look at this for a second, where can we find 6 zeros? So I see 1, 2. So we want this and then up. We would have 1, 2, 3, 4 with this 5, 2 pair. If we want to cross and oh, you know what we're not considering maybe? I think now that I'm thinking about it, I think we're actually missing, we're missing the one that goes like, it's like an L, it's like we did the L and we did this, but we actually have 2 more rotations of both of those that we need to do, don't we? Because we could have like going up and then across like that. Or we could have going across and then up. So that's probably where we're missing this is that we're not considering that case. You know what I'm kind of thinking we could do is like, so an easier way rather than, I'm almost like, rather than doing this again, we could just rotate the matrix. Like if we rotated the matrix by 180 degrees, then we could use our same code and it would accomplish, or no, we would have to rotate it by 90 degrees. Like we can copy this 4 more times or 2 more times to do the other variations, but that then becomes this like, okay, well, do we really want to do this 4 different ways? Can we or write the code 4 different times? Can we optimize it a little bit more? Here's one other idea. And this is like, so for each cell, there's basically 4 directions our path can go. It can go up, down, left, or right. And so rather than do all the L's, what if we computed the 4 paths that lead into every cell? And then we just looked at, okay, well, of these 4 paths, what gives us the, like, we could essentially combine our 0 counters in different ways, and then like essentially we would look at, okay, you are at a point, you consider, to calculate the paths in each of the directions, it's not that hard to do. We're going to end up with basically an array of 0 counters going different directions. So we're going to end up with 4 arrays going 4 different directions, and then we're going to have to combine them in different ways to figure out, okay, well, we would basically write a function for ourselves, or like we could add something to 0 counter that's like okay, let's combine 2 0 counters together. That might not be a bad way to do it. Rather than having to re-implement this. I mean, again, we could implement the other 2 directions. So I guess like, this is not this. I don't think this is a great strategy. But let's say, just for argument's sake, that we want to just get this working. So we have 2 other options. We basically have the big difference here is that we started with upper left, lower right. Now we want to go lower left, upper right. And so I think the big difference here is just going to be that it's going to be 2 things. One is that our column goes from, our starting column goes across, but then our row needs to be, well, our column goes across. What's the shape that we're looking at? It's not an L, it's not this. It's this, right? It's like a backwards L. And so the row, so we kind of go across the row and then we go up the column instead of down the column, right? That's essentially the difference. So instead of this, it goes I is greater than or equal to 0 and I minus minus. Otherwise, it should be the same. And then with this, it becomes like an R shape essentially. So we iterate over the column first. Well, no, Did I do this one right? I mean, we should really change the order here, right? I mean, if we want to do this like properly, it should really be like, okay, we're gonna start with, we're gonna, if we want to do this one, should be, shoot, hold on, let me think about this for a second. So if this is a backwards L, it's like let's iterate across the row and then go up. Okay, I think that's fine. Because that's going to create a backwards L shape. And then with this one, if we want to create an R shape, it's like we're going to iterate up the really, like if we're going to do it in this order, we should do I is going to equal grid 0.length. I is greater than or equal to 0, and I minus minus. Right, so we're starting at the last column and iterating over, and then we're going down here. And I think if we do that, it's our runtime error. Oh. And I'll comment these out for the moment, but this is going to need to be row minus 1. And which else is an issue? It's call minus 1. We're still, okay, where was this? 91. Oh, this was actually right before. I think, yeah, that's okay. So it's that, I think. All right, so yeah, so that I mean, that solved our problem here. And if we submit this, I think this should probably work. It's either gonna work or we're gonna, okay, what's happening now? Okay, so this is interesting because we shouldn't have failed any cases that we already passed, because this was purely additive unless we're getting our output's bigger now. I don't know. I don't really feel like debugging this, to be honest. Yeah, I think that like if I was gonna go back and redo this, what I would probably do would be to take that approach of looking at all those midpoints, where I would basically, what I'm gonna do is I'm gonna calculate all of the these like 0 counters going left, then all the 0 counters going right, then all the 0 counters going up, and then all the 0 counters going down. And I'm going to put those all into 4 arrays, and then I'm going to look at a midpoint, and I'm going to say, okay, let me look at the different combinations that I have available to me. I'm either going to look at like these two, or these two, or these two, or these two. And I'm going to write like a function to merge those, 0 counters, which is pretty easy. Is just sum up those values within them, right? Like we have the 10s, the 5s, and the 2s. We can sum those up. We can create a new one, right? And then just figure out which of those is giving me the max. And then basically I don't have to deal with all these different iterations and iterating through in different ways. It's going to make it a lot easier. The other thing, so I would consider doing either that, or the other thing that I might do is, again, like rotate the matrix, right? If we could keep our code the same and rotate it 4 times, where if we rotated it, then we're basically tackling each variation. And so that way, that might be an easier approach to avoid having to write tons of code that we need to reuse. But yeah, those are a couple things I would consider. Again, like obviously, you know, this is the case where, you know, sometimes we're going to take an approach and it's not going to be quite right, or we're going to miss something along the way. And this is where, you know, obviously should have taken a little bit more time on this one to think through and make sure that we were covering all our cases. And then probably, you know, taking a little bit more time to plan out, okay, how are we going to approach this? But hopefully this is helpful for you, because again, like, you're not going to solve all these problems perfectly. So hopefully this is helpful for you to have some context of how to think about the problem. And I'm going to go ahead and wrap things up here. Thank you for joining me as always, and I look forward to seeing you next week.